These diagrams basically give a better idea of how the alternating current and voltage works. When the voltage is positive, the current flows in one direction. When the voltage goes to zero, the current doesn't flow at all. And when the voltage goes negative, then the current flows in the opposite direction. These diagrams also show how Ohm's law still works for alternating currents, so that if we have a 5-volt signal, the 5 volts going into a 10 ohm resistor, the current for that is half an amp. So at that particular point in time, Ohm's law is still working. And that's how that works. Ohm's law works for any particular point in time. So for instance, for the peak voltage, that's equal to the peak current times the resistance, could be at any other time. Peak power is equal to peak voltage times the peak current. It's also true for any other point in time. But many times we don't want the peak current or voltage or power, but we're more interested in what the average power is being generated by a circuit. And here's how we do that. We get the average power in the following way. The power at any particular point in time is given by the product of the voltage times the current, or by the square of the current times the resistance, or by the square of the voltage divided by the resistance. And so what we do is we actually take an average of one of these quantities over the period of the alternating current. So the graph down below shows actually the quantity I squared R at any particular point in time, and so we actually average that out over one period. And it goes up to a value of 1, it's normalized to that. So it looks like the average value of that would be close to 1/2. And in fact, that turns out to be the case. And we'll look at that just a little bit more. This graph just shows what happens if you were to take the average value of the current, say, over the cycle of the period. It goes positive for half of the period, negative for the other half of the period. So if you actually took the average value of the current, you're going to get 0. And that sort of shows why we have to take the square of the current and take the average value of that over the period of the cycle. This shows that the average value of the I squared R representation of the power turns out to be 1/2 of the peak power, which is 1/2 times the peak current squared times the resistance. So that's kind of a nice result. It's just the average power is just half the peak power. But many times we want to know, well, what would be like an average value of the current, let's say a DC value of the current, that would give us the same power being dissipated as the average power. And that's shown on the next slide. The hypothetical DC current squared times the resistance, which would be the power being generated by this DC current, we set equal to the average power being dissipated, the 1/2 I peak current squared times the resistance. So then we can just divide through by the resistance in both sides and get that the DC current squared is 1/2 times the peak current squared. Take the square root of both sides and we get that the DC current is 1 over the square root of 2 times the peak current. And we call this hypothetical DC current the RMS current because RMS for root means square, and it's kind of the average current, and we got it by squaring the current, then taking the average of the current squared over the period of the cycle, and then taking the square root of it. So that's why we call it the RMS value. We also have a voltage, an RMS voltage, which we get by exactly the same way. Root means square, and so that's 1 over the square root of 2 times the peak voltage. And if we were interested in the power, the RMS power, that would be the RMS current times the RMS voltage, which would give us 1 over 2 times the peak current times the peak voltage, which is indeed exactly 1/2 the peak power being dissipated. And here's a small example. Suppose we had a source of 155 peak volts feeding into a light bulb that had a resistance of 15 ohms. It turns out that 155 peak volts corresponds to an RMS value of 110 volts. And that's what we commonly say when we say 110 volts AC. That's what we have in our houses. So with 155 peak volts, what would be the peak current? Well, using Ohm's law, V is equal to IR, or I is equal to V over R, we could say V of 155 peak volts divided by 15 ohms should give us a peak current of about 10 amps. And 10.3, I guess, is the right number. So what would be the peak power? Well, we multiply our peak volts by our peak current, which would be 155 volts times 1 times 10.3 amps should give us a peak current, a peak power rating of somewhere around 1550, or I guess 1600 peak watts. And then the harder questions, maybe a little bit. What's the RMS power and RMS current? Well, the RMS power would be just the peak power, so half of 1600 would be 800 watts. That's average watts. And the RMS current would be the peak current over the square root of 2, and so that would be like 10.3 over 1.4, and that should turn out to be somewhere around 7 amps. And I guess 7.2 amps is the right number. So that's about it for this, and we'll do some more problems next time.